transportation and energy system. And now Omar is actually going to talk about the intervention planning of such a connected system. So Omar, the mic and the screen is yours.
Thank you so much. First, thank you, Hiba, for the great presentation. I actually got many questions, but no time to ask, so I better run with my own presentation. So can you see the full screen?
Yes.
Great. So good afternoon, everyone. My name is Omar. I'm a postdoc at TU Eindhoven, and today I will be sharing with you our latest research work at TU Eindhoven, collaborating with Ahmad Reza and Claudia Feccarotti, who is also here today. So my presentation deals with the intervention planning and optimization of complex interconnected systems. I will be mainly talking about interconnected infrastructure because that's my domain of interest. And however, the logic behind our approach is applicable to most processes that can be planned. So you just have to do this projection in order to have it applied to your own case, for example. So this is the outline of the presentation that I'll be going through today. First, I will give a little introduction about today's topic, and I will say why it's important. Then I will briefly mention the problem that we are trying to solve and the objective of this presentation. This will be followed by the modeling and optimization approach that we have developed to kick this problem and solve it. And of course, I will show some interesting results we have obtained by applying this method to a realistic case. And finally, I would like to share some pieces of news that you might be interested in. So let's get started with the introduction. Yeah, well, before anything, I would like to start with the so-called system view, as it's an important concept for almost, well, every engineering application. So we as a human usually have a narrow view. So we tend to look at things from a close distance, and we are sometimes so focused that we are not really focused anymore. So we do not see the full picture because we do not force ourselves to look at things from a distance. And as a result of this, we miss on opportunities, unfortunately, because we are really limited to this narrow view that we have. So I would like to share with you just a little story of our neighbors here in the building who were trying to reduce the gas consumption in their apartment. So heating system is very gas consuming, and gas price is increasing, and their apartment was badly isolated. So they were losing a lot of heat quickly. So what they did to solve this problem is to better isolate their house from the outside, and they had to deal with a company to do this for them. Okay, and they paid a lot of money for that to get their house isolated. But after this, they noticed that the situation did not get significantly better. So after some investigation, it turned out that there was a lot of heat transmission to their neighbors with whom they shared some walls, for example. So it's not only with the outside. So of course, they do not have control over the neighbors' apartments because they cannot really force them to isolate the apartments. But they are still trying to convince them because they had already paid a lot of money and for nothing, actually. So the issue here is that what they did they did not look at the system as a whole. So they did not look at the system as the whole building, but they just looked at their own apartment and they tried to fix it on the local level. But this turned out not to be very effective, and it did not really yield the most benefit. And our world is just like that, but it's a lot more complex. So we cannot really just focus on one simple thing and forget about the other. Okay? So in this story that I just shared, it's obvious how having this system view can be helpful. It's, however, not as clear when it comes to complicated processes or systems because we simply cannot really see the benefit just directly. So in the context of infrastructure, which is our focus today, the resolution at which we look at the system, whether it's closed or whether it's system view, can really make the difference. So currently we have different infrastructure networks, and these networks are managed by different operators, okay? And every operator plans their intervention activities separately with little coordination with other operators. So they do not really collaborate a lot when they do the planning. Everybody does their own stuff. However, networks are really interdependent. Okay? And interventions in this context of this work can be, you can think about it like maintenance or replacement of components or any other activities. Everything can be called intervention. Okay? And as I will be showing in this presentation, the lack of integrated approach to manage all networks together as one system is really preventing the operators from getting the most benefits. So if we keep doing the things just separately, we are not going to reach the most benefits possible. So we have to do things together. Okay? So I would like to move now to the problem that we are trying to solve. So we have, okay, so I mentioned the intervention planning. So this intervention planning is the act of, planning intervention activities in specific time windows. Okay, so you want to decide when an intervention activity must be executed, in specific time horizon. Okay, that's a decision you would like, that's the plan you would like to make. This is intervention planning. And intervention planning can be coordinated or not coordinated. So for example, in the case of not coordinated, so we have this example where we have a time horizon from 0 to 12. Think about it as time step like month or year or whatsoever. And we have two different operators or managers of two different systems. Okay, so operator A plans their activity every 3 months, 3, 6, 9, and 12. While we have another operator, operator B, plans their activities every 4 months, like 4, 8, and 12. Okay, and they do not talk to each other, so everybody is doing things on their own. So, and we assume that this is one system. So whenever someone would like to do intervention, then the system will be unavailable. Okay, so here we have 6 system closure. So we have 1 for A, 2, 3, 4, 5, and 6 times. So 6 times we are going to close our system. Now, what happens if we do the coordination? If we do the coordination in the sense that we manage to group our activities together and to implement them in the same time step or time window. Okay, for example, we can move B to A, and we can move this B to A here, and A and B are already here together. So instead of having 6 different interruptions of our system, we will only have 4. Okay, that's of course intuitive because the system is very small here, but when it gets complex with several operators and with a lot of interdependencies, it's not really easy to do this grouping just like that. We really need a tool for this. Okay, so mainly our problem is that we would like to jointly plan intervention activities for multiple operators at the same time. So this brings me to the objective. So we are introducing here an integrative optimization approach for infrastructure intervention planning, okay, in multi-system and multi-actor setting. Multi-system means multiple networks. So water, transportation, transport network, and other networks as well. And multiple operator are the multiple multi-actor are the multiple operators. So different managers, different stakeholders would like also to see how this optimal plan, for example, affect every one of our stakeholders. Okay. So let me now show you how we really see our system and how we try to model it. So this is how we look at our system. These are the different components of our system. First, we have something called operator, which is the manager of an infrastructure network. Okay, an operator can be manager for one or multiple network at the same time. And a network is an infrastructure network, so it can be like transport highway network or water network. And every network is composed of different objects, or you can think about it as components of the network. Like if it's a highway network, then an object can be a highway cross-section. Or if it's water, then it can be water pipe, and you name it. Okay, and these objects here from different networks are really interdependent. It means that if one of the objects become unavailable due to maintenance, so imagine that you are doing maintenance for object 1, so it's unavailable, then it might affect another object like object 4. Object 4 becomes also unavailable because they are interdependent. Maybe they are in series, for example, so you have to have 1 in order to have 4 as well. So there is interdependency between them, and we try to capture this interdependency using adjacency matrix. We call it interaction matrix between objects in a simple way, because we try to keep things simple, to keep our method scalable, because we are working with infrastructure, which means it's a very complex system. If we try to really model everything as it is in the reality, then the method will be unfeasible to use. So apart from objects, we have also interventions activities. Okay, so intervention can be, yeah, as I said, maintenance, and it can be intervention for one or multiple objects at the same time. So for example, intervention 1 is a maintenance for object 1, intervention 2 is a maintenance for object 2 and 3 together at the same time. And we also capture these kind of relationships using kind of relation matrix, which is also adjacency matrix. We try to model these relationships using matrices as well. Great, so this is how we look at our system and the relationships between the different elements that we have. Now that I showed you how we model our system and the different elements, I would like to show you a bit more what I mean by interventions and objects using this example, which of course I'll be also using later on to show you the results. So in this example, we have a small network of a small interdependent network that's composed of 3 infrastructure types. So we have in green the highway network, and we have in blue the water network, and we have in brown here we have a railway small section. Okay, and as you can see, these objects or these components of the different networks intersect at some locations, and these intersections imply that there are interdependencies that we have to really accommodate. Okay, just to give an example, as you can see here, we have water pipe that's buried under, it crosses, it goes below one of the highways. So if you want to do maintenance for water pipe 1, then probably you need to excavate this highway, right? So you need to do some kind of excavation here in order to reach W1. So it means that if W1 is unavailable due to maintenance, also H1, which is not under maintenance, will be unavailable. So now it's really smart that if we could plan activities together now, if we also plan H1 to be maintained in the same time, because we are in any case, we are going to excavate it, right? This applies to a lot of other cases where we have interaction, interdependency between objects. So this is what we are going to take advantage of, these interdependency, in order to group activities and get benefit out of it. Yeah, okay, so I showed you how we model things, but now I would like to show you how we do, in simple terms, the optimization. So our optimization problem here is divided in 2 stages. First, we have stage 1, which is optimization, or it's a tentative intervention scheduling for individual objects. Okay, so we focus on individual objects, not the whole system. So imagine that we have 3 different objects, only 3. So we just focus on every one, and we try to find the best plan for that object using degradation model. Okay, so then we focus on another object, we find its plan, and then another object and we find its plan. So we don't really do the system view now that I introduced before, but we just look at every system, every component apart. Okay, why do that? Because this is first step for the global optimization. So we need to do that in order to know where we start from. So for example, now we can start from this preliminary plan in order to do the global optimization for the whole system together, for all object together. Now, just little exercise. Now, if I tell you to do the global optimization for this preliminary plan, what are you going to do? So how do you group these activities together? Yeah, maybe someone will say that maybe we can move B4 to here. We plan it with A3, and when we can move C2 to here, we can also plan it with A3, B4, we have them all together. B3, we can move it to here with A2, and B2, we can move it back a bit because it's now too close to B3. And maybe we can add another B here because the distance between B3 and B4 now is great. So from this, we get another plan like that. Okay, but now we have like groups. We have these together, we have these together, and we have these together. Okay, also we have this one alone. So now we have 5 system interruption, while before, if you count them, they are 7. So it's kind of we got some benefit of this grouping. But this is a simple exercise, right? Now, if things become really complex with many objects, I don't think anyone can really do this manually. That's why we need optimization to do this for us. And this is stage 2 that's going to do just this for us. So I just want you to focus on this. This is what the objective function of our optimization. So what we are trying to do is that we are trying to reduce our net cost. So we are trying to keep cost minimum, and then we can get the corresponding plan. Okay, so we minimize the net cost, which is divided into few terms. For example, we have the cost of interventions activities, we have the cost of service interruption, and we have the setup cost as well. Without going in details, all of these sum up to something we call the total cost or the net cost. That's something we would like to keep minimum. We would like to minimize in order to be paying less. Okay, and our problem is linear problem, which is great because it yields the best solution and the computation effort is low. So that's the good thing to know, of course, because it's a complex system, so we have to keep things linear. Great, just to show you some of the result that we got out of this. So this is mainly the main result that we sorry. Okay, so we're not seeing my mouse. Okay, so this is the main result we get out of this method. So what you can see here is the final intervention plan for all interventions together. So we consider a time horizon of 30 steps. So think about it at 30 months, for example. And here we have the 7 intervention activities of our case study. So it tells us, this figure tells us when every intervention activity must be executed. For example, intervention 1 should be executed in time step 1, then 4, then 7, 10, etc. Same for intervention 2, it should be executed at these time steps. And what you see here, this distribution is the best distribution because it yields the least cost for us. And this is what you can see, the cost you can see here in red. And this point here, so this is cumulative cost, of course, so it increases as time goes on. And this is the maximum cost, the total cost, sorry, which is, of course, the minimum cost because it corresponds to the optimal plan. Okay, so this is the minimum cost possible that you can obtain. But how better this is this compared to other conventional planning? We compared it to the normal approach that the infrastructure operators use. It's called individual approach. So everybody like plans their own interventions, and then we would sum up all the costs, and then we could get the total. And this is what we got. With the optimal program that we got from this tool, we got this amount, and it's 17% cost reduction. So we could get 70% savings just by better rearranging activities and grouping them. This is just to show the performance of our algorithm. So we show the computational time as the variables increase, number of variable increase. Just let me go back a bit. So here we consider 30 time steps. Okay, 30 time steps mean it took us like just 1 second here. But if we increase 30 time steps into 3,000, we would finish with 80 seconds, which is still great because 3,000 is very large number. Okay, so the relationship is kind of linear, which is great for such complex system because it means that our approach is scalable. All right, so what's special about this method? What's special about this intervention method is that it's multi-system modeling. It captures interdependencies between interventions of multiple operators at the same time. So it's not just oriented to one network or one system, but to all systems together. And it needs coordination to be able to apply it. And it's easily scalable. All right. Now this was the last slide of the research. I would like to share with you just some news that you might be interested in. So we are organizing a promising special session in the European Conference on Safety and Reliability, which is ESREL. And we have picked an important theme that tackles today's resilience challenges, and it fits with a broad spectrum of disciplines. So for those of you who are doing research in the same line and wish to go to Dublin, abstract submission is still open, so just feel free to send your abstract. Finally, next week I will be hosted by NG Infra, so Next Generation Infrastructure, to give a talk about my research, but also to be talking a bit about the concept of participatory system design. And the idea is to make the audience more aware of this concept and to highlight the benefit of this concept so we can get more people to adopt it and use it in the future. And you can use this QR just to get more information or to get yourself registered if you like, of course. Thank you so much for listening. And if you have any question.